I wanted to start on by talking about the motivation behind this work and my work in general. So I just wanted to give you a quick overview of explainable AI and the tools that we used in this work. So what is explainable AI? I'm sure that you've heard about it already. So explainable AI is the art of extracting explanations from automated systems, and it's been growing in popularity due to the rise of machine learning algorithms. And today, you can find sites offering explanations for things in general all over the web. So I just collected some screenshots here of explanations that I was offered, for example, on Netflix. So Netflix offers you an explanation for film recommendations, for example. This is an explanation, a human explanation for a fantasy football ranking. And this is an explanation for a chess game that was played between chess programs, so between artificial intelligence. This is a human reconstructing the reasons behind choices that were made by a computer, basically. And I find this really interesting. So we like explanations. We feel reassured by explanations. And this is a strong reason behind explainable AI. But I mean, there are stronger reasons behind this. I don't know if you are aware of this, but in 2016, there was a big deal around the Compass case, where ProPublica, which is a group of journalists, basically, investigated the use of these commercial algorithms to assess a criminal's risk of becoming a recidivist, and they found it was actually biased against Black people. And what I found interesting in that case was that you can find online the analysis at this link, and it's a really complicated and long-winded analysis. So it kind of involved human effort to automatically to extract an explanation that is given in terms of basically of statistics. So these are screenshots from the website, and I thought, well, it would be great if we could find algorithms to automatically extract these explanations. And I thought, well, perhaps this is just an American problem, let's say, a problem that is far away from us. But actually, it turns out in Milan, there is a software, Keycrime, that is being used by the police to predict crimes, which is kind of funny, right? Because they say it reduced the number of crimes in Milan by predicting when and where a crime will happen. But it's kind of funny. It kind of reminds me of Minority Report, right? So you can be charged for a crime just for being in the wrong place at the wrong time. So for all these reasons, we have a right to an explanation, which I'm sure you've also heard about, and I'm not going to enter the details of whether I agree with the right to an explanation, which entitles individuals to receive an explanation for a decision that was taken on the basis of an algorithm, basically. But you can see here there are quite good reasons for asking for it. So wrapping up what I've just been saying, basically the problem we are facing is that of having some black box system, so usually a neural network or some system that just takes decisions without having the possibility to explain them. So it takes a decision. It tells you, well, you must go to jail, and well, you end up wondering why. So the idea would be, especially in post-hoc explanation methods, we try to find transparent systems, so some kind of system that sits at the interface between the user and the black box itself, and so the system talks to the black box and tries to understand why the black box took that decision that it took. So you can think, if you let me draw a parallel, this is more or less the psychologist of black boxes, because just on the well, it's the behavioral psychologist of the black boxes, because it just talks to the black box. So it only has access to the input and output of the black box, and it tries to reconstruct the reasons behind the decision the black box took. And if you like, you can think of model specific methods as the neuroscientist of black boxes, right? Because model-specific methods, as opposed to post-hoc methods, try to enter the specific details of the black box, of how it is constructed, and tries to give you an explanation in terms of how the black box is made. What we are concerned with today, on the other hand, is something that is independent of the internal structure of the black box. So it can be applied to any black box. It can be a neural network, it can be a decision tree, it can be, I don't know, like a majority voting system, it can be an SVM, and so on and so forth. The post-hoc explanation method needs to figure out the reason behind the decision. So one of the inspirations for our work was LIME. That is one of the most popular algorithms in this field from 2016. And LIME stands for Local Interpretable Model Agnostic Explanations. And it's been extremely popular. It's gained more than, I don't know, like it's gained thousands of citations. And it's really interesting because, again, since it is model agnostic, it can be applied to any black box. So just to give you an idea of what the input and output of this system is, so you can feed the system with an image and obviously a black box that performed classification on this. and then it will output the reasons for classifying this image in a certain way by just highlighting the pixels that had a high impact on the decision. So, for example, this image was predicted by Google Inception Network, so a black box, so it was classified as electric guitar, acoustic guitar, and Labrador, because it clearly contains, well, we can argue that it contains a classical guitar and a Labrador, maybe, but maybe not an electric guitar, for example. So we may be interested in knowing why the image was classified as electric guitar, right? So the reason is for electric guitar is given in terms of these pixels. And you can actually see that this pretty much looks like an electric guitar. So this is the explanation for the electric guitar. These pixels here kind of look like a classical, an acoustic guitar. So we may take this as an explanation for acoustic guitar. And finally, these pixels, there is some noise obviously, but especially this set of pixels here show a Labrador. So this is kind of a nice algorithm, and it is really useful in cases like this, where you have predictions that do not match the true class, and this is a well-known case where. So the algorithm was trained as to distinguish wolves from huskies, and you can see it's kind of accurate, but in this case it got the wrong it produced the wrong response, the wrong answer, because it predicted wolf, but this is actually a husky. And applying lime gives you this explanation. So it was possible to see that the algorithm was actually classifying huskies and wolves not on the basis of the animal itself, but it was predicting the class using the background. So it was basically a snow detector rather than a wolf and husky classifier. So if we go back to our diagram.
Sorry. Yeah. Sorry. You said it was predicting not on the basis of animal features, or not only on the basis?
No, it was just
just detecting the snow.
Basically, this is what it was doing, because you can see that the wolves have the snow on the background in this data set, where there is no snow in the huskies pictures.
Okay.
So basically, they trained the algorithm. They thought, oh, we have a nice classifier. But then applying lime showed that the pixels that were significant for the classifications were not those of the animal, but were those of the background. So this is really interesting, right? Because I mean, you can clearly see that, well, the classifier is quite efficient in this case, but it is performing classification for the wrong reasons, basically. So you can, when you get these explanations, you can go back to the algorithm and try to fix the problem by giving it more examples in this specific case, or I don't know. You can change classification methods, and you can try to do something at that point, right? So yeah, I think it is useful to do this kind of benchmarking. So going back to our diagram, so the idea behind LIME was to use a specific explainable model as the psychologist, so to say, of the black box. And this model was the linear model. So it constructs a simple linear approximation of how the black box functions, and it outputs the result of that linear model to the user. So I mean, I'm not entering the details of how this works because it's not my work. But so my idea was, well, I mean, this works with a linear model. Why don't we use logic instead? And I was working at that time with, I was playing around really with a system that is being developed by Mark Law and other collaborators at the Imperial College London. And this system is a machine learning system that learns logical theories from the data. And so learning logical theories is really useful because logical theories are kind of easy to explain, sort of. I mean, we can discuss about this, but they kind of are. And at that time, it was being applied to all sorts of things directly on the data sets. So it's a really interesting system because, for instance, let's say that you have several instances of a graph that contain a Hamiltonian circuit. So here you have a simple graph that has a Hamiltonian circuit in it. You can you can easily see that it has one. So it's a graph with 3 nodes and 4 edges, one from 1 to 2, 2 to 1, 2 to 3, and 3 to 1. And this pose here says that this is a positive instance. So it is a graph that actually contains a Hamiltonian circuit, but you can feed ILASP with negative information. So you can give it a graph and say, well, this graph doesn't contain a Hamiltonian circuit. So you give it a bunch of graphs. And the interesting thing is that it learns a logical theory of Hamiltonian circuits. So this is a theory that defines Hamiltonian circuits, and it is being automatically learned from the data, so from a bunch of graphs. So you can think of this as a machine learning algorithm that learns something that is a logical theory, okay? And it is interesting because it is transparent, but the problem is that it is not as efficient as machine learning algorithms, okay? So a neural network is much more powerful. Well, powerful is not powerful, it's much faster, say. so you can learn more complicated things, because it's implemented in a way that can be run on GPUs, and therefore it is kind of it can perform many computations in a very short period of time. So to give you an idea of what else ILASP can do, they applied it, for example, to cases where users were walking around and doing things in a video stream. So they were performing several activities. They were running, they were dropping objects, they were meeting, and so on. And the idea was to learn some complicated activities from the low-level activities. So just starting from their position and so the direction they were facing, basically. Okay. And from just this information, we wanted to learn some more complicated activities. And ILASP was, for instance, was able to learn some high-level activities, such as meeting. And not only that, because that, even a machine learning algorithm can do that, but it was possible to learn rules that were kind of easily explainable. So now I don't know whether, I will zoom in, but it was learning things like, so these two people are meeting because one is walking, the other, so one is walking, one of them is walking. The other just appeared, and they are closer than 24 pixels. So it is not just giving you the decision, so to say, that purple and pink are meeting, but it is offering also some explanation for that. Okay. So this is really powerful, and again, it works very well. But again, it is not, so it is learning event definitions from the data. But my idea was, well, why don't we use ILASP to talk to the black box and try to construct a theory that matches the behavior of the black box, rather than applying it straight to the data. Okay. So, and this is just in a nutshell the idea behind.
Sorry, yes. Fabio. Can you say again something more about how works ILASP? That I didn't get very well to this point. As you will explain in the future, I don't know.
Yeah, sure. So do we want? So do you? So basically, let's assume that you have many of these graphs, right? You have just the, so you don't really have the definition of a Hamiltonian circuit. You want to know what's common among all of these graphs, okay? So you have a bunch of graphs like these. And basically, ILASP, what it does is to do, so it has a clever way of trying to find what are the axioms that kind of cover all the examples that you give it, you provide it with. Okay. So so it kind of so the naive approach would be just to try all the possible axioms. So you try all the possible theories. You find some way of enumerating all the theories, which is kind of unfeasible, and see whether they admit these graphs as their as the model of the theory you are considering. Okay. So basically, what ILAF does is it generates a theory. It considers its models and see whether the models of this theory cover all of the data. So whether the
so I understood that the ILASP is highly top down, and
yes,
it is quite explainable because the theory is clear.
Exactly.
Yeah. Okay.
So you get a theory of this form.
Mm-hmm.
And then you can, so if you may have some automated way of transforming this into natural language, right?
Okay.
So it is basically trying to learn a definition for examples, for a set of examples. And yeah, it is kind of explainable because yeah, we can assume that theories are transparent, but obviously if you end up with an overly long theory, you can argue that is not explainable, but you can try to, so ILASP has several parameters that you can set up, and you can try to look for the shortest theory that describes your examples. In that way, it kind of implements Occam's razor, right? So yeah, so it tries to find the shortest theory. So it does not do brute force, but it has a clever way of searching theories. And at the end, it gives you this type of output. And in the case of people walking around, again, it finds theories of this type. So obviously this originally, this definition of the activity meeting had was in the form of axioms, of a logical theory, but it was then transformed into something like this. Yeah, exactly. And actually, well, what it figured out was a definition of this kind in this case. So two people stop meeting if one of them disappears. So the system has information about whether some people disappear from the video, and it uses that to construct a definition for the meeting activity. Okay. And then it has.
So it was ILASP was developed as a machine learning algorithm, and the new idea is to apply black box to explain.
Exactly. Okay. So the new idea is that this was kind of applied to data. So we had there was a lot of information about people, so people's position, people disappearing, appearing, people walking, and so on and so forth. And that was used to construct high-level activities definition, okay? But that was applied directly to data. So the new idea was, well, why don't we use this, why don't we apply this to black boxes rather than from data, okay? So in the original use, ILASP was applied to data rather than black boxes, okay? So in this way, we can, I thought, well, we can try and so let ILASP talk to the black box somehow and try to construct a theory that reflects the behavior of the black box, okay? So we train the black box on the data, and then we let ILASP talk to the black box. I'll give you an example. So in the original paper that I'll give you the reference at the end, we did some preliminary experiments. We implemented SVMs, which are a classical algorithm, classical machine learning algorithm that is usually regarded as a black box. And we trained it on a data set that is commonly used for small tasks. So we trained these SVMs, so these black boxes, and then we let the SVM learn a preference relation between sushis of different types. So we had users telling us whether they preferred, I don't know, some type of sushi, I don't know, nigiri, salmon nigiri, over something else, over tuna hosomaki, whatever. So the SVM at the end was able to predict whether the user preferred some sushi over another. And these models were kind of accurate. It had around 80% accuracy. But then obviously these SVMs are not explainable, okay? So we picked 10 of such SVMs, trained SVMs. Each of them was trained on a different user. And we applied ILASP on their output rather than directly on the data set. Because again, one could just, if you have the training data, you could apply ILASP directly on the data set. But let's assume for 1 second that you only have the SVM. And this is very similar to commercial, so to the case of Compass, right? Because you have the commercial algorithm, but you don't have access to the data set that Compass was trained on. So you want to kind of extract explanations from Compass. And then we performed 2 tests. We used ILASP as a global approximator. So we wanted to see whether we could get a general explanation for how the SVM behaves in general. And then we did experiments with ILASP as a local approximator. This is similar to the Husky and Wolf problem. So in ILASP, you provide, in Lime, you provide the system with a specific image of a husky, and you want an explanation for that specific image, right? So why did you classify this image in such way? So the idea is that we weren't expecting ILASP to behave very well as a global approximator, but we wanted to try anyway. And so just to give you a flavor of what the data set was, so what the features of the data set were, I'll show you an example. So the each sushi was characterized in this way. So for each sushi we had information about style, major group and minor group. There are, well, some other features. So whether it is seafood or nothing in this case, minor group, that it is a categorization which is given in terms of an integer from 0 to 11. But then we also had some categorical features. It's oiliness, price, and so on and so forth. So then the data set consists of a bunch of pairs of this form here. So SI, SJ, U, where U is a user and SI and SJ are two sushis described in terms of these categories here, of these features here. And this pair means user U prefers sushi SI over sushi SJ. So this is what the data set looks like, right? So the SVM, so the black box is trained on a lot of these pairs, and then at the end it is able to predict pairs of this form for unseen data. Okay, it is able to predict whether the user prefers a sushi over another. So at this point we had an SVM, so a black box that was a representation of the user preferences, basically. And what we did was to query the black box. So we queried the SVM about several pairs of that form. So what we did was to ask basically the black box, do you think, in this case, user 1 prefers sushi S1 over sushi S2, where S1 and the S2 were randomly generated in the feature space. And at this point, we had a lot of classified examples. We constructed a lot of pairs that were the result of the classification by the black box. And we trained ILASP using these examples. And we constructed a theory that does not correspond directly to the user's preferences, but it corresponds to what the black box thinks the user's preferences are. So, for example, without entering the detail of ILASP syntax, of ASP syntax, actually, so we had a series of axioms that tells us, well, the black box thinks that the user does not like sushis of minor group 3, and this is the first priority. So it gives you a bunch of axioms that are ordered according to an order. So this is the first most important axiom. This is the second axiom, ranked by importance again, and so on and so forth. So it kind of this is a negation symbol. So it seems that the SVM thinks the user doesn't like seafood. This means that the user, so the SVM thinks the user doesn't like sort of expensive, this means expensive sushis of type maki. And this one means the user doesn't like sushis of, well, no, sorry, it does like sushis of minor group 9. Okay, so we have this theory, and we can study how much this theory kind of matches the behavior of the black box. We did experiments, and we kind of reached around 80% fidelity, which isn't that good, to be honest, but we were sort of expecting that. But you can do better by playing around with ILAS parameters. So in later experiments, we reached actually 90%. So what does this mean? This means that our theories are able to explain the underlying black box, so they match the underlying black box up to an 80% degree of accuracy. Okay, so sometimes these theories are just wrong in 20% of the times. And so global approximation is kind of difficult, but what usually people do in explainable AI is to do local approximation. So what does local approximation means in our scenario? I give you two sushis. These sushis are described, let's say, in terms of these two features, two feature sets. So S1 has style 1, major group 0, minor group 11, and so on and so forth. And the same for sushi S2. And let's say that the SVM tells you, I think user 3, in this case, prefers sushi S1 over S2. Okay, and we want to know why. Our procedure has a clever way of sampling around S1 and S2, so it makes the black box consider sushis that are kind of similar to S1 and S2. We construct a theory of why sushis similar to S1 and S2 are being classified in a certain way. And in this way, we are able to reconstruct a reason for saying that S1 is preferred over S2. In this case, our explanation is that the black box seems to favor sushis that are more oily. And you can see that this corresponds to the truth, since S1 is more oily than S2. Okay, so rather than just saying S1 is preferred to S2, we can say, well, according to the black box, S1 is preferred to S2 because S1 is more oily than S2. So in this way, we are kind of able to provide an explanation, and local explanations are actually very reliable. So we reached well, more than 95% accuracy for this type of explanation. So at this point, I've given you a kind of general and non-technical overview of the system, but you're free to reach out to me with more questions. Just wanted to end on a note about current work. So we are currently doing a comparison of ILASP with respect to other ILP approaches. There are some other machine learning algorithms based on logic that do something very similar to what ILASP does. We are comparing them. Use FastLASP, which is the latest version of ILASP, which is much faster, so we expect it to be more accurate. What's very interesting, I think, about our current work is that we are trying to build more, well, I wouldn't say realistic, because the sushi data set is a real data set, but we want to build bigger data sets and more complicated black boxes, because we consider the SVMs, which aren't really very complicated, but we are now trying to apply these systems to neural networks, deep neural networks, and we expect it to work, to have worse performances on neural networks, but we want to see whether we can actually use ILASP in that context, and whether we can improve scalability performances using some kind of techniques like dimensionality reduction to mitigate the effect of complicated complex data without losing transparency, though. Another interesting thing that but this is more future work, we would like to apply this to convolutional neural networks and the problem of artificial vision in general. Just on a last note, I just wanted to give you the main reference for this talk that was published 2 years ago now in the proceedings of KR, and you're free to access it at this link. I wanted to acknowledge the people that I am currently working with, so especially Matteo, who is an assistant professor at the University of L'Aquila, and Daniele Fossemont, who is an MSc student that we are supervising together with Luca Raggioli from the University of Manchester, and they are are especially dealing with the black box part of this work. And to finish with, I just have a small question to ask. So we are currently in the process of building a bigger data set for so more. It is again a preference data set about food, for Italian food, and if you could, it would be great if you could access this questionnaire and complete it. It takes around 10 minutes to complete, and that would help us construct this food data set that will apply and use for an extended version of our paper. So with this, I am done. Okay, I forgot the last slide, but